first lesson on fundamentals of gestural interaction. In this presentation this afternoon, I will more or less introduce the basic concept of gesture recognition, from very basic gesture to more sophisticated ones, and I'll try to also share with you some experience that we gained with gesture recognition. I will not detail all algorithms, but I'll give you a sneak preview of them, and I will also finish today with some guidelines about gesture sets, because there are different problems. But before starting, since we are not too many, please feel free to ask any question at any time. And maybe I'd like to have a few words, to hear a few words from you, if you have any particular interest. So for instance, if you have a specific aspect of interest, then I may want to develop it further depending on what you're saying. Who is going to start? Maybe you?
I don't have a particular topic.
Apart from 3D gestures, okay.
No, we're just master students who integrate user interfaces.
Okay,
so
great.
Like very high levels, so you want to see more in depth of the
All right, that's fine. Is it the case for all of you? No.
No, I don't think so. It's a mix.
And what about you?
It's the same.
The same?
I would like to know how are once you identify the gesture, how do you program them?
That's a very good question. I will partially address that, and especially I will see how to progressively switch from a programmatic point of view to a non-programmatic point of view, so that you no longer need to reprogram or to retrain the for a while, because otherwise it's very time consuming. Okay?
I'm more interested on how to integrate gestures in existing tools.
Do you have any particular tool in mind?
My tool, for example.
Okay, great. What about you?
I'm interested in gesture in recognition for my master's thesis. I work with Vanderdonckt.
Okay.
And he told me it would be interesting, so I don't really know exactly what I'm looking for.
All right, we'll try. Do you have any particular interest about gesture recognition, so that if you have one, then I can maybe also elaborate on some of these aspects?
I work with augmented reality and virtual reality, so it will be like the interaction between the application or the user interaction with the machine.
Okay, so you're mainly interested by 3D gestures?
Yes.
Okay. So again, good afternoon, thank you very much for coming. You are very courageous today, because not only the weather, but also the circumstances are not so appealing. So last time, I said that in principle, a gesture, at least the way we understand it, is any movement of any part of the body. So even if I'm doing with my head, even my shoulders, any part of the body can be a gesture in our understanding of each eye, which is not the case in other disciplines, like maybe psychology or whatever. So for instance, not only full body gestures, but for instance, recently we also conducted a study to ask people what type of gesture would you like to do with your head or also with your shoulders. And what we, interestingly, because I'm a computer scientist and not a physicist, I asked a physicist what kind of movement do we have with the head, and I discovered we have 3 axes. First, I can move, of course, if I keep my neck constant, I can move my head this way, of course. If I no longer keep my neck constant, I can do this, so I have a little bit more flexibility. And if I enable, while my torso was constant in the second, if I allow my torso also to be flexible, then of course I can bend even more. So I discovered that we have actually 3 types of movement in any direction. So in the end we had a taxonomy of all of the head gestures that are technically, at least physically possible, but having a gesture that is physically possible does not mean that it's acceptable or easy to perform. For instance, we found out that bending gesture, especially in this way, it's okay, but to the back it's very difficult because of our neck, and laterally you need some flexibility. So for small gestures like this or like that, it's okay, but for repetitive, it's of course very tiring. What I will also introduce is what type of dimension. Usually we say that 0D, a 0D gesture, according to my definition, is only 1 point. For instance, if I tap something, or if I push a button, this is a 0D, because I have only one state, on, off. So this is one point. If I extend this, a 1D gesture means I have a linear path. For instance, if I move my finger on the table to adjust the volume up and down, this will be a 1D gesture. If I enable, for instance, to use the entire table, then I may progress to 2D, and of course then X and Y coordinates are usually captured for any gesture, like maybe for surface computing or for whiteboard, especially. Any coordinates are of course flat because of the constraint imposed by the platform. For 3D, so this is more or less for your case, and you have, for instance, it could be a stroke in the air, so in this case I only have the X, Y, Z and T aspects, but maybe for you, since you're working in augmented reality, you may go to even more complex gestures, like 4D, 5D and even 6D. So this means that, for instance, let's imagine that I'm using this platform, so this is a 2D surface, so if while I'm moving and I'm doing a gesture, here I'm producing a 2D gesture, but I'm moving again. So of course these points can be characterized by X, Y and Z in 3D, but since it is on the surface, then I consider it as a 5D gesture, because I have 2 coordinates from here, and I have 3 coordinates of my movement. So this is different than, for instance, performing a mid-air gesture like a path like this. And we can go to 6D, which are very complex. These days, I have only seen a very few studies about 6D in that case. 5D and 4D is okay. Another example, last year we had also a funny one. We asked with people from KU Leuven, maybe you know them, from David Geertz. No? No, and there was another, not Catherine Verba, but the other one, I will remember. They have developed an interactive cushion. So the cushion is sensitive to the pressure, and it is equipped with electrodes that you can push at any place, and then you can of course bend it, you can curve it, you can push it, you can squeeze it. So this is a 6D, because of course the cushion itself, if you don't move it, then it's 3D, or maybe 4D with the pressure. But if I'm moving my cushion while doing gestures on it, I can go to 6D, which is of course very complex. In my vocabulary, I will use basically 2 classifications. First, a stroke gesture is a series of points. So this is a stroke. Even if it is in the air, for instance, I know that you're dealing with a stroke gesture recognition, but in 3D, which is not like, for instance, hand gesture. Also, we are separating, for instance, well, mostly I'm a right-handed person, so this is my dominant hand. My left hand is the non-dominant hand, and I can perform either disymmetric gesture or symmetric gestures, or even disymmetric gestures. This is also very important when we have different devices. If you remember maybe last time, when I introduced the ring gesture that is no longer commercialized by the Japanese company because they failed about the gesture coordination. If we give people 2 rings, they can perform maybe a gesture with one hand, with 2 hands, in a symmetric way or in a completely disymmetric way. But of course, disymmetric bimanuel, the last one, is more complex. Of course, we are all human and we tend always to perform gestures which are the easiest one from a physical point of view. So one hand, which the manual, my dominant hand, and with only one. Now, especially also for 3D gestures, one of the most up-to-date taxonomy that I'm using, so this is particularly useful for you. This is a taxonomy that was done by Microsoft people some years ago, which is still a reference taxonomy for 3D gestures. So I'm no longer talking about just strokes, like saying, okay, this is okay, or no. So their taxonomy is from England, etc. They have this representation, which is basically decomposed into 5 categories, which are further decomposed. So the first one is pointing. So this is very simple. I'm pointing, for instance, this table or this projector. So it's a pointing or the gesture. So this is not very complicated. The second one is the Semaphoric. So we have three subcategories in this case. The first one is a static one. So I give a position with my hands, for instance, say stop. But I no longer move my hand. So in this case, it's called static semaphoric. Dynamic, for instance, if I do this to rotate an imaginary button, so even if it is physical, it is referred to as a dynamic one. And a semaphoric strokes, like, for instance, when I'm using my smartphone, we are used to do something like this to delete something in the list. So this is a third one. Now, more complicated, especially into 3D. Manipulation gestures is any type of gesture that is intended to transform the environment that we have. So, for instance, if I move my handle here, this is this type of gesture because it's no longer a movement in the air. It's something that I want to transform, like opening the door, or flipping this, or clearing, or whatever. So it's to transform the world. So here is a video. If you're interested, you can discover the video on the web also. They capture several examples of this gesture. I will switch to this one. Do I have sound?
Normally, yes. No?
No.
But it's on the HDMI, you normally have it on the HDMI.
Okay, anyway, not a problem.
Hmm? Aha, or to the projector. Aha, for the sound there, could be.
Maybe some keys to go.
Oh, then that's not a problem.
There might be a separate cable for the sound.
Normally it should work with the
Yeah, but
HDMI.
the loudspeaker, not on the projector.
Otherwise, I don't mind.
Oh.
So what we know is that gestures are in principle very rich in terms of expressiveness, because we can use not only our full body, but also we have much more flexibility, and not surprisingly, the gestures that are the most common or the most used are the one with most mobile lines. Like, of course, our hands are very good. Like, for instance, supination is something like this, and pronation is something like this. Supination or supination in English, or I think it's the same. It's like, I want, please, I beg you. So any line can be used, but of course some parts are more difficult than the others. If I have to use my legs, I can of course have some flexibility, but I will not spend hours doing feet gestures. What is interesting is to think that the gestures can be also equivalent of shortcuts for something. We all know, for instance, if I'm using Alt F4, I will close my window or application, so this is a shortcut. But let's think also that the gesture could be a shortcut in itself. Like, for instance, if I say cut, I can do a cutting gesture like this, so it's look like I'm using a shortcut, which is a gesture, to refer to a command that will be triggered by the system. Or, well, we are all used to have the pinch out or pinch in to zoom in and zoom out, so this is more or less a standard de facto gesture today. Or tapping or panning. So like, for instance, X, C, V, which are, of course, the three letters that are close to each other. So this is a physical mnemonic and not a semantic one. So we can think about gesture as being also equivalent of shortcuts. But even more, you could think, and this is interesting work also, we can think that any menu or any command could also be attached to a gesture. So gesture could become even themselves shortcuts. So this is a work done by Caroline Appert from Invariant in France some years ago. What they did is that they built a dictionary here of gestures, a simple one, like L, a curve, or whatever. And then what you could do, you pick one from the library, you can rotate or you can expand, and you say, for instance, this will be my gesture shortcut for this command. So imagine that you are the user, you want to say cut, copy, paste. You want to use your own gestures. Well, it's not exactly your own gesture because you have to choose them from the dictionary, but at least you have the choice to do it. It's not imposed by the system. So you say, for instance, this one will be cut, so you select it, and then it becomes now in your library, and you say you can attach it to that command. And then you can practice here to say, okay, I'm good enough, and the system is well trained. Indeed, it can be recognized. So it gives you some parameter here. So the nice thing is that by doing so, you can attach, in principle, a gesture to any menu in Java. So here, for example, they developed a music player, and they were able to replace any menu or menu items in the menu bar by a gesture that you could issue on any surface. And the benefit of that is not just for the fun of it, but also why? Because people remember the gesture much more than the shortcut from the keyboard. For instance, if I have to say, well, Control P for printing, that's okay, but maybe Control Y for cancelling it, because you know why it's Control Y for cancel? The Y stands for Yanks, which was a very old command from Unix, and they said Y was for Yanks, and Yanks is it's an uncommon use for saying cancel. So this has been transferred to our keyboard, but nobody knows, almost nobody knows that. Second thing is that when people are defining their own gestures, they can create a vocabulary that is 3 times much better than a keyboard. So if I have to create shortcuts with my keyboard, I can do it. I can parameterize that. But if I'm going to attach gesture to my shortcuts, people can have a vocabulary that is 3 times more in terms of amount of gestures, and the recall rate is even better, whether they are doing it by mouse or by pen. As you can see here in the vocabulary, when the gesture is issued by the pen on a surface, it's more efficient than with the mouse, not surprisingly. But this was at the time when the mouse was still used. So pen-based gesture, just as it's a particular category where I have a stylus, a pointing device, and not necessarily my finger. An interesting device that we have also used, but is not, our experience show that it's not so efficient, is this one, which is a mouse with a pen combined. So imagine that you have a pen, like Ulrich is using a pen, but at the top of the pen you have also a mouse. So if you want to use your pen, you can draw, and if you release the button, then you can use it as a mouse. But it's not such, well, maybe it's sufficient for some cases. However, for instance, with pen, an area that is very promising, I will detail that also next week in the design cases. This is for user interface sketching. User interface, especially graphical one, are very straightforward for people to sketch. Why? Because everybody can sketch. And surprisingly, we conducted a study where we compared designers on the one hand and end users on the other hand, when they have to sketch interface on a whiteboard, something like that. Surprisingly, we found out that the end user were better than designers to draw or to sketch user interfaces to be recognized by the system. So here you can see that some people are sketching on a tabletop different parts of the user interface, and the system can recognize that automatically. But when there were designers doing that, the recognition rate was not so good. Why? Because they were so used to do fine things that they were over-detailing the design, surprisingly. And the end user, they don't care, they just sketch, okay, this is, for instance, so this is a label, and then this is an edit field, another label, and then this is a drop-down list, and that's it. So they just sketch things very simply, as opposed to designers who say, this is my name, then the prompt, and it is my first name, so they do everything very finely, aligned, then very nicely designed, maybe with some mask, etc. So they do it so finely that in the end the system does not recognize them very accurately because it's over-detailed. Anyway, but I will detail that later on. A few words about vocabulary. So a stroke is a series of points. Either it could be on a surface, or it could be in the air. And a pen-based gesture is just a time series of strokes. So for instance, if I'm issuing this gesture with my finger, let's say, I'm a surface, and doing this gesture, the corresponding strokes will never be a continuous line, because of course the pointing device will sample my gesture and will capture a series of points like this. Well, usually it's a little bit more than that. Because if I'm doing this gesture, let's say, this is my starting point and this is my direction, the device that I'm using will probably sample more points at the beginning, like something if I start here, it will sample more here, but since I will accelerate, the sampling will diminish, and then since here I have a maximum and then an inflection, then again it will capture more, and then something like this, then something like this, and in the end I'm stopping, so I have more. So the problem with that is that some points I have here regions where I have many points, and some others I have not so many points. So the gesture is not continuous. So this is why we need to have these strokes, and so these lines that are representing, like for instance here I have a lot of points, and more or less too many points that are unnecessary, and here I have not enough. So I have to interpolate. What we can do also is identifying the shape of the gesture. I think I told you that I have a very good example. For instance, a bandit can imitate my own signature very accurately. So if I say this is my signature, for instance, after a while, a false person can imitate my gesture, my signature, because it's a physical shape. But when it comes to characterize all the different movements also with the pen, then it's almost impossible to reproduce, because I'm the only one who knows how to accelerate and how to decelerate. So this is why we take not only the shape, but also the motion. So the motion characterizes the motion of the gesture. Unistroke, it means that I have only a one stroke for a gesture. So like for instance, if I'm using my smartphone, I'm doing this. This is a flick, or a unistroke gesture. If I'm doing several things like, as I have to write a A, I can do one stroke and a second one. Or if I have to a B, I can do it with one stroke, or I can do it with 3 strokes. I have multiple possibilities. We can have, of course, different directions. If I'm writing the B, either I can do it in this way, for instance, then I start it from here and then from here, or I can do it in the other way around, like for example, like this one, and then something like this. Think also about people who are not writing from left to right, but also from right to left, like in Arabian language. So basically these are these definitions. So you use stroke, you have only one, multiple stroke you have more. It can be one direction, for example from left to right, or many directions. A flick is a particular gesture that is always a unistroke, but with one direction. For instance, when we do something like this is a flick. Whether it is on the right, on the left, on the top, or on the bottom, or any direction. It's only one direction. One flick, or combined, it becomes a mark. So a mark is a particular type of gesture that is usually made of several strokes, like this one. For instance, if I say, first I'm doing a flick on the right, and then it will trigger, let's say, a cut, copy, paste menu. And then if I'm going up, then it will say, this is copy. If I'm doing one again on the right, then it will make cut, let's say, or the other way around, and paste for the last one. So for instance, for pasting, I have to do something like this. So this is a marking gesture, or a mark, because I combine flicks in different directions. So, but these are very simple gestures. Now, if I'm considering the same shape, for instance, in the few slides that I will show you, let's imagine that I'm doing this shape, right? Very simple one. I have many possibilities to draw it, and people have very different ways to do it. Like I can do it in one stroke, or in several strokes, in one direction, or many directions, or even a combination that is completely crazy, like this one. Down flick, another flick, then a mark, another flick, and then an arbitrary stroke, then another mark, and then another mark to finish it. So this one is of course completely crazy, but it's very challenging to recognize. Even if the gesture itself is just like this, it's simple. So this leads to several properties. So for instance, these properties that I will introduce now in a few minutes, they are very important throughout gesture recognition, not just for this case. The first one is called stroke invariance. It means that if I'm doing this gesture, or if I'm doing into 2, 3 or more parts, the gesture is itself the same in principle or not. So for instance, I may want to say this is this gesture. So the system should be, to some extent, invariant depending on the strokes. But we'll see that later when we'll see the algorithms. Some algorithms are better for unistrokes, some others are better for multiple strokes, or some others are completely independent. You can do the same with the directions, whether I'm issuing the gesture from left to right or right to left, it should be indifferent. But not all gestures make this difference. A third property of invariant is called the sampling, which is very much due to the device that I'm using. If I'm using my finger, or if I'm using my mouse or a pointer, or even if I'm using a laser pointer, and I have to move like this, for instance, you can see here the raw gesture that is captured with as much points as possible will give this star, but if I'm reducing the sampling to 32 points, then it will give this one, 64 points like this one, and double, I will have more or less a complete one. So this is not just a problem due to the device, but it's also a problem for the recognizer later on, because if I have more points, like this one, of course it will be more precise to be recognized, but then it will become slower, and sometimes the drawing or the gesture that is issued here will be too detailed, and then over-constraining the recognition, so that it will be almost impossible to reproduce the same star, the 5-branch star, in the same way, because of course there are some local deformations. So today it's better to use something like between 32 and 64. Most of the recognizers today, even including ourselves, we try to focus on 32 points. It's not needed to have more. The problem is that if you have this raw gesture, how to choose the 32 points? Especially when I told you that here in the beginning I have an aggregation of points, and here there are not so many, so we have to find out which one. A second consequence of the operating system, but also of the device, is that there is a problem of lag. The system has some latency. So, depending on the device, for instance, here on the whiteboard, it's straightforward. If I'm doing a gesture, you will see it continuously. But if I'm using some slow device, and I will use a red color for that case, while I'm using this gesture, the system will not show immediately my gesture. So it will be something like this. So while I'm using here, it will be something like this. So which is very disturbing. It means that the red gesture will be slower to be visualized than my own one. So this is sometimes disturbing, especially on low-hand devices. Well, of course, on very good smartphones, you no longer have the problem, but on low-end device, we have seen that, for instance, we have 2 branches, so depending on the strokes, in the beginning, the system can sample a very good point, but after a while, then, as you can see, the performance will decrease. So we have to stick to a maximum, otherwise it's impossible, and then you have too much latency, and the problem is that in the end, the user is completely confused. She's drawing something, like this one, but the system only visualizes or represents a few points, and it's a little bit with some delay. So this is like invariant, but it's more or less due to the device. A more important one is the so-called translation invariance, is that if I'm drawing a gesture, it should be recognized wherever I'm issuing. If I'm issuing on this whiteboard, on my smartphone, or even on my trackpad, it should be the same. But this is a big problem today that we are trying to solve. It's called the transferability. For instance, let's imagine that you are the user and you define on your smartphone your favorite gesture, like for instance a Z or whatever, a spiral, let's say. Okay? So you define it on this device. What would be nice is, after that, to transfer your gesture to any other device that you will be using, so that you no longer need to train the other one. So if I'm drawing a spiral here, I will be able to use it on my tactile screen, or even, why not, on the whiteboard, or even on the wallboard. And I no longer need to retrain the system for the same user, for the same gesture. But that's another part. So translation invariant, it means anywhere I should do the same and it should be recognized. Second problem again is the scale. For instance, if I'm always referring to the same gesture here, I can of course have transformation along the x-axis or the y-axis or both. So for instance, here also are deformations. But would my recognizer or would my gesture be recognized as well if I'm applying some deformation? Well, it depends. Some of them are invariant to scale, fortunately. So if this is my reference gesture, then if I'm doing deformation like this one, it will not affect the recognition rate. Or maybe not, it depends. The last one is rotation invariant. Is that, as you can imagine, if my reference gesture is something like this, but if I'm now, instead of drawing my gesture in this way, I'm doing it in the other way, then rotating with 90 degrees, and then with 180 degrees, especially if people are working around the table, the gesture will no longer be the same. Maybe if I'm here, I'm gesturing. Of course, my gesture will be the same if I'm here, but for the recognizer, there will be some rotations. So again, we could have rotation invariance or not. A very challenging one is skew inference. Is when you deform the gesture, as you can see, but also with lateral or bilateral deformation. But this one is very challenging today, and there is no solution yet for that. I mean, no universal one. So in order to show you how a recognizer can be variant or invariant to these properties, let me show you an old one to understand you it better. So here I'm giving you the example of the X-stroke gesture recognizer, which was developed for Unix some years ago. And the principle is like this one. Initially, you have a drawing area, which is decomposed into a 3 by 3 matrix, and any gesture should be represented in some traversal of these regions. Maybe you remember edge right, maybe on what was again the Palm Pilot. Maybe you have used in the past some Palm device. No, you're too old now. You did? Yeah. Okay, great. So maybe you remember that on the Palm you had a very specific region where you had to gesture. So if your gesture was another area, it was not recognized. So this is the same principle here. So basically, the gesturing area is decomposed into 9 cells, and any gesture will be then represented as a series of cells traversal. So for instance, if I want to do a horizontal flick like this one, then it will become 4, 5, 6. If it is here, it will become 7, 8, 9, or 1, 2, 3. If I have to do a vertical flick, then I can have 1, 4, 7, 2, 5. So for simple gesture like this, it's straightforward, and the accuracy was very good. However, when you come to consider many people who are, of course, issuing things differently, especially, for instance, if you consider the 7, I don't know, how do you draw a 7? Do you draw it something like this? Or maybe you draw it something like this, like American people? Or some people are also doing it like this? Or some people are something like this? There are different ways to express just a 7. So of course I can record all these variations in the system, but then it will increase the complexity of the gestures recognition. So for instance, if you consider the B, here you can see different possibilities, like starting from here, doing this, or starting with the vertical. So here I forgot the vertical stroke, but here I have the vertical one, etc. And then a combination and even a return. So in this case I have to record all these variations. So the advantage of that is that, as you can see, if I'm representing this gesture as a string, it will become this one. The second one is that one, and the third one is that one. And as you can see, you have many substrings that are common. So the recognizer is not too bad, because there are substrings that are common to these gestures. So it's not too bad, but anyway, it's not sensitive to all of these variations at once, so it needs to be recorded. So stroke invariance, it is not, because it's a unistroke recognizer. You cannot do something like a third gesture here, and second one here, and then the third one there. The system does not take that into account. However, the direction invariance, it is not. So if I'm issuing this gesture or that gesture, it's different because of course the first one will be 3 to 1 or 1 to 3, unless you record all variations. So if you consider that 1 to 3 or 3 to 1 are equivalent, or 6, 5, 4 or 4, 5, 6 are equivalent, then it becomes invariant. Again, this is my responsibility as a developer to record all of these capabilities. And now if I'm considering, for instance, somebody who is writing from left to right, then I have to invert all of them. So in the end, I have a lot of combinations just for one gesture. So this is not very efficient. In the end, I have to record all of these variations, and some of them are even more tricky. Like for instance, if I say this diagonal flick, so in principle it should be 1, 5, 9, if I'm doing something very nicely. But of course people don't write this very finely all the time, and they have some variations, like for instance they go until 2, and then in the middle here, and then etc. So if I'm doing 1, 2, 5, 6, 9, it will be no longer a diagonal flick, but it will be a mark, like something like this. So confusion, and the accuracy is no longer very good. So in this case, it is not direction invariant. Regarding sampling and lag invariance, it depends of course on the software, but again, I can, if I'm doing my gesture very quickly, for instance, the gesture can capture a few points in the first cell, nothing here in the middle, and then something here, and then the system is completely fooled because here there is a big hole, and then there are 2 strokes, and the system doesn't recognize multi-stroke. So no recognition. For the last 3 properties, translation, scale, and rotation. Translation, yes, because you have 2 modes. Either the gesture can be issued in a dedicated window, like in the palm. You have to draw it here, or you can use it in full screen mode. This means that you can use any part of the screen, which is of course much easier to do that, although it's obscure. Scale invariance, yes, as you can see here, but of course there is a bounding box to be done. Rotation, no, unfortunately. If I'm using the G and I'm drawing my G something like this, it won't be recognized again unless I'm recording all variations. But it's not very efficient. So later on, Dean Rubin introduced the first, let's say, machine learning based algorithm for stroke recognition, and Professor Singer has used it extensively, not only this one but also the 3D version and the improved version, so there are several variations on that. Basically, it says that a gesture is an array of points, x, y, or even z, with a timestamp, or even with more features. So these days, especially these days, there are people who are adding a lot of features so as to improve the recognition with other parameters than just the points. Like for instance, it could be the velocity, the tangential acceleration, or even the shape. Like for instance, if I have an inflection point, or if I have a variation, something like this. So people are adding some more features. The problem with that is that of course I can use more features, but then the system becomes even more complex to use for people to develop. So this is not maybe desirable. The original algorithm from Rubin was based on 13 features, so we're not detail all of them here. So there are trigonometric formula. Like for instance, this angle, which is alpha angle, so we have to compute its cosinus and sinus according to this formula. So this is the angle between the first point and the third point. So the initial point is here. This is x0, so this is the first one, the second one, and the third one. And then it computes the angle between this one, but also with the other one, which is almost the last one. This is this angle beta. So the problem with that is that why Dean Rubin did use this feature? Well, he said, I think that this angle is representative, and this other one is representative. And why not, for instance, that one? Or for instance, why not that one? Of course, he tried many features, and this combination was still efficient. Especially for clustering. So the idea is that once you have classes of gesture, you can make a cluster and say, okay, all of these gestures will belong to the same cluster, the same group, and then the system is a classifier. So you can use classifier techniques for doing so. An example of a very good software that did that from this one was the work from Mohammed and Othman from University of Freiburg in Germany. They automatically performed several variations for scale, translation, and rotation invariance. Like for instance, if you see this one, maybe initially it was like a circle, but of course nobody can draw a perfect circle unless you're a very good mathematician and then you have a very good arm that is perfect. Some people can do it, I'm not. So here you can see many variations and they are all grouped in the same cluster. So this is nice because all of these variations, even this one with a small variations like a real line, is classified in the same category. And the system classifies all of them in different clusters. This one, for instance, is very tricky because this is the gesture for erasing something. So if I'm saying, of course, I draw a B and I want to erase, or I want to do something like this. But of course, people are performing the same gesture with many variations. Like some people are doing something like this, some people are doing something like this. So there are many variations so that in the end the recognizer cannot recognize them all. And here they introduce several variations and you can see that whether it is with some lateral deformation or vertical deformation or even both, they all belong to the same cluster, which was very good at that time. So to sum up, the Rubin algorithm was okay for translation invariance, but not for scale and not for rotation. A little bit later on, when, for instance, Microsoft introduced the first tablet PC in 2001, this guy, Mr. Seiger, working for Microsoft, introduced a very simple one, algorithm for recognition that was, at that time, not too bad, and saying any gesture is represented by a set of directions, like this is up, right, down, left, down. Of course, it's a very simplified way to represent gesture, and still today there are people, especially for instance in Italy, they are still working with these kind of things, and it's not too bad. So for instance here, if you say LU, it means left, up, and then up, up, or and then up, right, etc. So in the end you have a string like this, which can be programmed. So for instance, if you want to program this Seiger algorithm, it's very straightforward. It's something like this. So to recognize a question mark, you only need this with this toolkit. So it means that, as you can see here, the upper red arrow is recognized by vectors dot ups, so it corresponds to that. The right one corresponds to that. So here it's like each stroke is matching first vectors up and then right and then down and then left again and then down. It's a question mark. So it's straightforward to write it, but it's not straightforward to be recognized. So the recognition rate was about 70%, especially because people had to write that very, very regularly. So that was still in 2005. As things are improving, 2 years later, we introduced a generalization of that based on a distance from Levenstein. So Levenstein is a Russian mathematician. And instead of having just up, down, left, and right, we said, why don't we use all directions? Like up, right, left, down, but also northeast, southeast, southwest, and northwest. So a gesture is then decomposed into a series of segments indicating any directions. Like for instance, this gesture is northeast, so this is 1, so 2 times 1, 1, and then the 2 is just this one, 4 times, and in order to do that, we apply a grid on top of the gesture, and each segment is then applied to each cell, and in the end, we have a string. Like for instance, here it will be 1, 1, then 2, 2, 2, 2, 3, 3, 4, 4, and then until here. So in the end, we have a string something like this. In this case, I have a string, so 1, 1, 2, 2, 2, 2, 3, 3, so forth. So any gesture is in the end transformed into a character chain. And in order to compute whether this gesture, for instance, is the similar as a previously recorded one, we have all the other strings, like maybe there is one, let's say 1, 2, 2, 3, 1, 4, 4, 5, let's say. So the system computes the so-called edit distance between those two strings, which is done by Levenstein. So if you Google Levenstein, you will find out this formula. Basically, what you have to keep in mind is that it is a measure to compute to what extent two strings are different. The Levenstein distance is very much used in information retrieval and also text search. Why? Because, for instance, if I'm typing some word and I made a mistake or misspelling, they can find out similar words by using the Levenstein distance. And this is also used, for instance, for also sound recognition. For instance, I have a funny story about that. Some years ago, I had to leave Brussels to Spain. So I had a course in the afternoon in my university, and I had to run to the Brussels International Airport. So I arrived there, and I went immediately to the Iberia counter and said, okay, I have a ticket to Valencia, and here is my name. So, and then of course, I have a Flemish name, and they typed it and said, I'm sorry, we don't have any ticket for you. I said, no, I'm sure. The secretary has bought my electronic ticket, so I'm sure that I have one. No, nothing. And then I said, could you please have a look? And then she tried again, but no way. They said then, yes, you had a ticket, but it was 2 months ago. No, not this way. So you have to go to the Iberia office and then to solve your problem. So I was, of course, shocked because I had to run, and my plane was just in 30 minutes. So I ran to the Iberia office, and I asked them, can you check that with my name you don't have any ticket? And said, no, I can't find it. And then I remember, maybe you can use Levenstein distance. Well, I didn't say that to the for woman who was there, because of course she will probably say that I'm crazy. But then I asked, in the Iberia software, you can do a search by similarity. So instead of, because my last name is writing in one word like this, Vanderdonckt, and for her it was very difficult to spell, but what happened is that not only they broke it into 3 parts, but then they wrote it here with D-O-N, and then I think it was with a Q. Of course, from a syntactic point of view, it was impossible to find my name like this. But then I asked, can you try the search by name, but with similarity? Because I knew that the Levenstein distance was there. Of course, I didn't tell her, because otherwise she will say that I'm crazy. And then she typed something like this, my real name, and then asked find by similarity, and then she found that it was another spelling. Why? Because the registration was done by phone, and the person didn't catch my Flemish name correctly, so this is what happened. And so I was very happy, I had my ticket. So thanks to Levenstein. So I have to thank this Russian mathematician. So in the end, it's the same here. Like for instance, even if I have a complex drawing, like this one, I have a long one, all of these segments of line are captured by a string, and then we can compare the value. So here is an example. Let me see. Yes. So there is a formula for that. It's not very complex. It's just about 5 lines of code. So if you want to use it, it's not very complex. And it says that each time I have some variations, I can add a cost -1 or +1. Like for instance, here you can see that 1 and 1 are the same, but 1 and 2 are different. But it's not different because here we have a series of 2. So here it will maybe withdraw something like a -1, and here we have still 3, so this is okay. So even if we have maybe 4 more, so here it will maybe withdraw 1.5 or whatever, because this is not so important. And in the end, it computes a similarity between 2 strings. So we have used it, for instance, for next week, when I will show you how we can sketch user interface and the system recognize that for you. We have used this technique quite efficiently.
How thinking, how did they handle conflicts, like between, for instance, detecting so O and the 0. Did you ever have a problem detecting certain characters because you could not differentiate between?
So the shape is different, but the size is different.
Yeah.
So
Or maybe people just someone wants to draw a 0, it doesn't.
if indeed if a same person writes a 0 and an O like this way,
Yeah.
so there will be no differentiation. Of course, I have to do something that is different. But if I have to make a difference between an O like this and maybe an uppercase, then it will be the case. Why? Because we apply a grid. So if we apply a grid like this one, and on that one, the string will be probably the same, but not on the grid. So in that case, it can distinguish between the uppercase and the lowercase. So here, for instance, you have a complex drawing, and in the end, it looks like this change, and then every shape is recognized. The nice thing is that it is even multi-stroke. Like imagine that you have first, I'm drawing a rectangle like this one, and then I'm adding a straight line, then I'm adding triangles. I can do that at any time. So even if my shape change over time, the system will detect that this zone has been changed and will recompute the recognition. So for instance, again, if I'm drawing it here, if I'm drawing a rectangle, okay, it will be recognized like a rectangle, but if later I want to say this is no longer an edit field and I'm adding here a triangle, the triangle will be recognized, but since it is inside an already recognized shape, it will be combined by this one and then add it. And then the recognition engine will start over and will distinguish not only the two individual forms, but will combine them together, which is very efficient. The drawback of that is that, again, it is not rotation independent. It is scale independent, it is position independent, but not rotation, unless you record all variations. It is not very complex, like for instance, if I want to apply a 90 degrees rotation, I have only to convert strings, so it's not complicated. So for 3 rotations, I need to apply just 3 transformations. The problem is that if I want to use only those 3, that's okay, but if I want to use all variations of rotations, like north, south, west, east, northwest, etc., then I have to introduce 8 more, and that's for each template, so this is much more complex. So in the end, for instance, in the test for recognition rate, for instance, when it is user dependent, after, as you can see here, after 2 templates, we arrive about 97–98% of recognition. But when we have to use it in a user independent way with all of these variations, we only arrive around 75, which is not acceptable today. Today, to have a very good recognizer, you should have at least 95%. Okay, this I will skip for a minute. So just to finish on this part, and maybe I will make a short break, because the next one is quite different. So I've introduced you to some of the basic recognizer, and some of them are still used today. It's not because they are bad, but of course they should be used in more specific context. If you look at machine learning, especially from AI, there are many other techniques like hidden Markov chains, supervised, unsupervised, supervector machines, feature-based neural networks, or even the most popular these days, or the CNN, and the convolutional neural networks. But they pose several challenges. Is that they work perfectly for the same category of gesture. Like for instance, if I say I want hand recognition based on image, if I'm recording all the images before, the system will learn these gestures and will recognize them very accurately. But if I have to use now, instead of my right hand, I want to use my left hand, I have to record all of this movement of my left hand. And if I want to combine, I have to take all of these images. So I have to learn or to train the system with all these images. So in the end, those techniques, although they are very efficient, I would say, even especially CNN, they can reach very efficient recognition, but they face challenge. First, in order to operate a CNN, well, not every day we can operate a CNN, and not everybody can do it. It's very complex. Second is that once it is implemented, it is difficult to debug and to train. If I give you, for instance, the right hand, the left hand. Now if I'm viewing this way, and then if I'm viewing both hands, the system needs to be trained for all of these variations, which is very time consuming. Also we need to treat several parameters to give some flexibility. And the most demanding one is the risk of what is called overfitting. Is that if I'm recording my right hand in this way, in front of the camera, the system will be almost perfect, maybe 99%. But if I'm using small variation, like something like this, something like that, or my hand like this, or like that, it depends, then it will be perfect for this situation, but as soon as I'm introducing some variations, it will no longer be good enough. So this is the problem of overfitting, is that especially for some papers, I have seen some other people publishing very nice papers say, well, in these very specific conditions, we reach 99%, 95, something like this, and we outperform all other recognizers. Why? Because they overfit the context. They said this is a very specific context, so the system was so much trained and so well trained that, of course, there is no problem of recognition or confusion between. And last problem that we will address maybe after a short break is that as soon as, if I'm the end user and I want to introduce my own gesture instead of the gesture that has been recorded in the system, I can do it, but then the system needs to be remodeled, retrained, and then rerun. Of course, today, there are especially dynamic convolution neural networks can do that at runtime. And they are very efficient for that, but still you have to do it. So if I have to introduce my own gesture, I have to say now to the system, okay, now record my own gestures and all of this variation, and the system needs to be retrained. And the problem is that if I'm giving this system now to another one, it's no longer working. So this is why, after a short break, we will now address the problem of some other recognizers which have the capability to stay simple, more or less, and also to accommodate new gestures without changing the code. So for instance, for you, if you want to implement a stroke gesture recognizer, and you don't want to modify it each time a new gesture needs to be incorporated or changed, you can use some of those. So this is what we will see after a short break. I will explain the basic principles of the okay. Any question or comment so far? Don't hesitate. Alright, so here I wanted to show you two videos now that we have the sound. The first one on how to attach a gesture to a menu item, or menu bar. So that's what's done from the menu shortcuts. So here, as you can see, the person is adding a new function like open playlist in a media player and picks a gesture from the catalog and maybe apply a rotation or maybe translation. And this is another one. Unfortunately, as you can see, only the catalog from the left can be used to add a new gesture. The system cannot add your own gesture. And when it is done, you can practice on the right. Let's see. And after that, you can practice to check whether every gesture that is recorded is properly recognized, yes or no, like a spiral. And in the end, you have some instructions in order to incorporate some special lines in the Java code, which are detailed here. I will not explain that. And in the end, you recompile the Java application, and you have now, as you can see, not only the traditional menu items, but also the shortcut commands, which can be issued on any part of the graphical interface. So here for play is just right, pause is left. Well, this can be questioned whether it is because doing pause like this is maybe backward and this is forward. I don't know. Fast forward, something like this. I disagree with the design. design, but that's not the question here. Okay, so now you can issue gesture on any surface. Okay, and then the system plays music. And you can even have the catalog of the gesture for this application, like opening a playlist, playing this track. And you also have the tooltipping gestures, like you have for tooltip for manual shortcuts, for keyboard shortcuts. So the idea is very nice here, is that on any action you can attach a gesture that you can issue on any part of the user interface by adding just a few Java lines with the tooltip. So this is very, very nice.
I think you could even do it we did it in Gecko, which was a part of iGesture, and you could even do it without changing the code, because you can in Java you have an API to simulate any menu interaction you have, so then you don't have to do any changes to the actual code. And you can also execute, that's also what we did on the command line, so you could not only control Java programs, but you could actually issue any low-level commands actually, which can of course be dangerous if it formats your hard disk or something like that.
Well, it depends on the
but there, I mean, I completely agree that it's super powerful if the user, they can define their gestures, and it can even be, from what we have seen, it can be very powerful for the 0D gestures, because imagine you still use the mouse, then you can, for example, use the mouse buttons for commands, so you can do like copy paste by just doing a gesture with the buttons itself, so you never have to, because if you use another gesture you still have to leave the mouse, but with this you can just move on with the mouse, and by clicking you can copy and paste the text.
That's right, and then you even keep the physical proximity, because when it is cut copy paste is Control X C V, because of course these are three keystrokes that are close to each other on the keyboard, in the same case as you are saying with the mouse.
But I think it's really powerful, and it's not seen that often that you can define. I'm sure you come back to that later, and how to define the gesture set, so that users should be more able to define their own gestures.
Right, but for instance here in this example, as you have seen, they have chosen the right arrow to have the forward, right? And as far as I remember, they've chosen this one for backward, which is strange from a design point of view. I'm not talking about recognition now. So you could say probably this is forward and this is backward. And now there is another recognizer called $V, which takes into account also not only the size but also the speed. For instance, if you say you want to do it fast forward, you can do a larger gesture, or you can do it faster. And the faster you do it, the faster it will forward you. So instead, for instance, if I'm using my remote control on my TV, usually you have to push it several times to make it faster, like 2 times, 3 times, 4 times, etc. So here, in one command, you can designate the speed of your fast forward or fast backward, depending on the size, but also the speed, the velocity of the gesture. But then you have to be able, you have to say, you have to be trained a little bit, because if you do it this fast, well, you no longer know whether it will be 4 times faster, or 6 times, or 10 times, or even more. But you just see the result, and then you can slow down progressively until doing that. So this is another way to design gesture, but this is a design point of view, not the recognition. The recognition is not a problem because it takes into account the shape, but also the size, but not the velocity up to now. A second example that I want to show you, and of course I will come back on that next week, but still at least to give you the flavor of it. So this is a software called SketchXML, which is a system where you can sketch with a pen, a stylus, or a mouse on any device. So you can use your own smartphone, your tablet, a tabletop, and the system recognizes the gesture for you and creates the code in HTML, for instance, for your user interface. So if you want to give people the autonomy to create their own interface without programming, you can do it. So here is an example of how it works. here the person has drawn a square and then a right line. So it is beautified and recognized as a single line. So the system recognizes the widget for you. So this is again a checkbox. And this is, for instance, what you can see. So not only the system beautifies the shapes for you as soon as it has been recognized, and here you have the hierarchy of widgets that are recognized, and at any time you can switch to generating HTML. In the past we were generating Zool, Java, and HTML, but these days only HTML5 is supported because the system is rather old now. And in the end you have something like this. And you can also say, for instance, if you want to designate this is a text area with multiple lines and you are not happy with the gesture because you forget it or it's not your own gesture, you can override the system and say either you just replace it or you add your own. And then for this purpose you have a drawing area where you have to provide 3 templates. With 3 templates we reach recognition about 95%, so it should be enough. So here, for instance, the person says, well, in order to draw a text area, I would prefer a spiral or whatever, another representation. So the system records the new gestures, replace it, and the new gesture is then added to the system, and then you can use it later instead of the previous one. And here for the moment we'll see that next week. In this sketching tool we have a gesture for about 30 different widgets, ranging from simple ones like checkbox, radio buttons, push buttons, until carousels, spirals, tab dialog box, etc. And for this purpose we completed a so-called elicitation study. So it means that we ask people, not designers, not developers, we ask real end users what kind of representation would you like to have in order to represent a checkbox, a list box, a menu, or whatever. And so we complete that, and in the end we have sometimes 1, sometimes 2, sometimes 3 different representations depending on the answer we got. So these are all incorporated in the system, and the system uses the Levenstein-based algorithm that I've shown you some minutes ago. So now let's go back to the last generation of stroke gesture recognizers. So these days, while there are many efficient algorithms for gesture recognition based on machine learning, there are other recognizers, especially known as the members of the dollar family, and there are several variations of them, and even other recognizers which are variations of them, and with improvement, optimization. I will not detail all of them, but you have to, if you have to keep in memory at least one, keep in mind the members of the dollar family, and the last ones are the $P plus and $Q, which are all variations. Basically, they all exploit the same technique, which is the nearest neighbor classification technique, which is a popular technique from pattern matching. So there is no secret here. Nothing has been invented from machine learning in this area. So this is a popular technique from pattern matching, which is roughly like this. First step, you have to build a training set, which consists of a set of templates. So you ask a series of people to record gestures, like here, you have a bunch of them, and they are all grouped by classes, like for instance this and that, maybe they belong to the same group, same class. This and that, they belong also to the same class, although there are different variations. So you build a so-called training or template set. And then this system will use this template set to compare any other gesture that will be issued later on. So this is the first step that is done beforehand. Second step is that you have to define a similarity function or a dissimilarity function, which compares two gestures, like for instance this one and that one will give a score of 0.1. So it means that it's likely that they are dissimilar by maybe 10-12%, but here it's very likely that they are dissimilar because the score is very high. So this is the second step, define a similarity or dissimilarity function, and in the end you just compare the figures by, if you have a candidate gesture here, you compare with all of them or the members of the classes, and then in the end you keep the only one that has the minimum or the maximum score depending on whether it is a similarity function, so in that case you want to maximize it, or a dissimilarity function, then you want to minimize it. So they are all using the same technique. Graphically speaking, for instance, if you have several candidates on the plane, for instance, you have several candidates with different measures, and you have a candidate that is located here. So this is the basic principle of NCC. Then you draw a neighbor around the candidate, like this one. And then you see, if you have a candidate gesture and you have three other ones that are close to this one, you may want to compare with these three ones in order to identify whether it is this gesture, that one, or that one. We don't know. So for this, again, we keep. So this is the candidate gesture that has been produced now at runtime by the user, and there are several other candidates from the training set to be compared. And each time there is another one, like this one, for instance, is a reference from the training set. It's almost similar, and they compare point by point the two, and in the end, it looks like the reference gesture is more or less similar to the candidate gesture. Even there are some variation, but from the points that are characterizing the gestures, it looks like they are similar, so it is recognized. So this principle is straightforward, and there's been several variations. I will not detail all of them, but just give you the flavor. The first one was the $1, which was basically a unistroke, so it means it can only recognize strokes, gesture made of one stroke. But the recognition rate was very good, 99%, with only 3 samples. So this is very good. The drawback of that is that it is only a unistroke. So for all the basic gestures, for instance, it's very good, it's very efficient, but as soon as you have many variations, it's no longer the case. So this is why they introduced $n for multiple strokes. After they recognize that, for instance, if you want to draw X, you can do it in many ways, like you start from here and then one, or from below, or you combine. So there are multiple ways to, of course, to issue the same gesture if the shape is the same. So in that case, the $n introduced a way to recognize all of these variations, and always with 3 advantages. The distance is the Euclidean distance, so the geometric interpretation is not too difficult to understand. It's only 200 lines of code in JavaScript, so it's not hundreds of lines and toolkits with libraries, APIs that you need to develop. And you have them in Java, you have them in C++, you have them in JavaScript. So it's quite straightforward to reuse. You have just to go to that web page, you can download the code, and in almost a few hours or a few days, you are done with it. So that's the second one. The third one, and they say that it's not just multiple strokes, but also different combination of strokes, different orderings, or even, for instance, if you want to consider a square, these guys, they have tried to distinguish, and they came to the conclusion that probably there are 442 different ways just to draw a circle, depending on how many strokes you have, how many directions, or how many combinations. So in that case, instead of introducing the system with all of these variations, they introduced the idea of a cloud of points. So instead of saying, for instance, we have to record this one, then that one, and in the end we will come up with too many variations, they say, now they simplify the shape of the gesture by a series of points. Why? Because in this case, it is completely independent of any ordering, and you have just points, no order. Whether you do it in this way or that way, no problem. So it's a very simple and straightforward idea, but very brilliant. It's just to replace a gesture by a series of points. And then you compare just two arrays of points, which is a very fast algorithm. In this table you have a comparison of them, but I will skip that for a moment. And there are a bunch of them after that. Now, today, in all of them, you have to keep in mind the $P plus is the most accurate one. So if you want to use it for maximizing the recognition, this one is the best. It's $P plus, which is itself an optimization of several predecessors. And they have also introduced $Q, which is an optimization for low-end devices. Why? Well, maybe not for my, although it's an iPhone 6, but for some low-end devices like mobile phones or very old smartphones or even for smartwatches, the processor does not give you a lot of computational power. So with $P plus, it works, but it takes until 30 seconds to recognize a gesture on a smartwatch. So of course this is not possible for the end user. An end user cannot wait for that time. So what they did is they did introduce even another optimization based on the cloud points, and they give it to $Q, which is the fastest one today. This is not as precise as that one. This one is the most precise, the most accurate one. I think it's 99.5% in any condition, so this is probably the best. And $Q is not the best, but it's the fastest one, especially for low-end devices.
Does it mean then with $P you're reducing it to offline recognition? So you could not distinguish swipe left and right anymore because
No, it's still online.
But you said you only see the point cloud, so how can you distinguish them between a swipe
In that
left
case, indeed,
and right? It would look the same, so I cannot
that's a
distinguish
drawback.
anymore.
These were the next slide. That in the end, since you replace every shape like this one.
So you throw away the temporal aspect.
Yes.
So it's offline
right.
actually. But
So in the end, for instance, if I'm replacing this by this series of points, okay, I can still distinguish that this is a right arrow, but if, for instance, I move it in another way, for instance, I no longer have the size, I no longer have the velocity, I have no, for instance, if I'm doing this and then that, it's lost. So if I want to say, for instance, I want a different gesture between those two, I cannot distinguish them.
yeah, but that's why I mean, even just the most simple one, which is just a line to the left or to the right, you could not detect it anymore. I assume with that. Okay,
That's
so it's again,
but on the
for specific sets it works then much better, but for simple ones it might not work.
I was thinking if nowadays in the smartphones you can unlock your phone with a gesture.
Yes,
I was
that's right.
thinking it would be, because someone can look and see, like thinking it could be extra interesting to have also velocity in there, but with this method you cannot do this.
No.
Okay.
That's one. But the gesture that you are referring to, it's a traversal zones.
Yeah.
Basically, because usually you have 9 points, and like the X true that I've been referring to in the beginning, and then you imagine a path like maybe this one. This is your own gesture, but again it's a traversal. And
But you could easily add the temporal aspects. I mean, as you said earlier with your signature, then it's much more
of course you can
secure
add
because that's
the
hard to.
velocity.
Yeah.
Maybe not for the Z, but if you have a little bit more complex, it will be your gesture, and probably nobody else will issue the same gesture with the same velocity as you do. Probably. So basically, there are, all of these recognizers are between points because they characterize between points of difference, and they say, if those two series of points are close to each other, then it's like they are similar. There are other people who introduced vectors, like instead of computing the difference between points, they said they want rather the directions. Like for instance here, instead this is a nabla, this is this sign. The nabla is the inverse of a delta, which is just a downward pointing triangle. Then instead of computing all the points, they compute vectors, and then they compare vectors. So it is not too bad, but it's a unistroke. Penny pincher is the fastest one, but it is a unistroke. Again, it can distinguish between different strokes. So we are working right now on a new family, which is based on vectors. So this I will skip in a minute. Okay, let's imagine that I have 3 points, A, B, and C, which are 3 points of a gesture. Say this is the starting point, the second point, and the third one. So between these 3 points, it forms a triangle. And of course, there are different ways. You can draw ABC, BCA, BAC, BC, and then BA, and then AC. So all of these variations can be captured into one single triangle. So the basic idea of our last algorithm, which is called FTL, is that if we have 3 points belonging to a gesture, they make a triangle, and instead of comparing the vectors of points, we would like to compare triangles, like this one. So the formula is this one, but let's keep it for the moment. Basically, keep in mind that, for instance, do you think that those 2 triangles are similar? Of course, they are not, they are different, but do you think that they are similar? Or to what extent? So, similar depends on the definition.
I mean, there is a right angle somewhere between 2 lines.
Yes.
Yeah,
Maybe this one is more or less the same one here, although I'm not quite sure that it's a square one. This one maybe is, I don't know. So it depends, of course, of your definition of similarity. But if you say that those 2 triangles are similar if they have same side ratios, more or less, so it means that, for instance, this angle is similar to that one to some extent, with some tolerance, of course. It should not be exactly the same, because, of course, this one will be probably 90 degrees, but this one will be 88 degrees. And then for the other ones, but also not just for the angles, but also for the distance between the different points. So if we compare 2 triangles, and if we compute their similarity, we have much more capabilities to express differences, because we take into account the angles and the distance between the points. So we introduced a formula, which is that one. So it looks like it is a complicated bit. Once we have done it in JavaScript, and it's about 50 lines of JavaScript, so it's even shorter than $1. It has been introduced by our colleague Paolo Roselli, working with a special distance. So computing the difference between 2 triangles is just this formula. Well, I will not go into details, but the nice thing is that we introduce a new distance, which is a distance between shapes. So here are triangles, and Mehdi is working on the generalization of that, but for 3D, which is much more complex than 2D. So again, there is another formula for different directions, and in the end, it goes something like this. So let's imagine that you have on the left a training gesture, and on the right a candidate gesture that you want to compare with any sample from the training gesture. You isolate a series of points, so the PI from the training and the Q from the candidate, and you draw all triangles like this one. You do that for training gesture, and this can be done beforehand, not just at runtime. You do the same with the candidate gesture, and you come up with a series of triangles that you want to compute their similarity one by one. So instead of computing this one is that one is that one, we compare similarity of the shapes, which is, on one hand, the advantage is that it is more expressive, but on the other hand, it's more precise. So it gives a series of triangles on the left, and a series of triangles on the right, and then we compare triangles by pair, by applying the formula that you have just seen. So by computing the similarity, then we have first pair of triangles, then second, then third one, and the fourth one. So for each pair we do that, and we just cumulate the scores. So in that case, for instance, the first one, they say that the blue rectangle from the right is more or less similar. It's 2% similar with the left one. The second one is 4%. The third one is even lower. And in the end, by computing, we just arrive to a figure saying that those 2 gestures are similar by 9% of chance, which is straightforward. In order to compare that, we conduct some experiments where we compare the one that we have seen before, like $1, $P, and our gestures on a very popular dataset. I will come that on in a minute. It's the Nick icon. And the nice thing is that we reach 95% of recognition, which is aligned with $p, so it's not too bad. So it's more or less the similar in terms of recognition, but the nice thing is that yes, but it is much faster. It is about 4 times faster than $p. So for instance, here are two algorithms, and you can see that the blue one and the orange one are much faster than $1 and of course of $p. $1 is faster because it's a unistroke and $p is multistroke. Interestingly, if I come back now on that one, we compare the recognition rate of all these algorithms, and not surprisingly, some gestures are complex. But then when they are complex for all recognizers. So they are all challenged by everything. Like for instance, this gesture has been considered as the most complex one. As you can see, the variations are very high. While for instance, this gesture, the fire, all recognizers have a 100% of recognition rate, which is just perfect. So interestingly is that all the 4 recognizers that we have compared, they give the same results. But when it is a difficult gesture, they are all challenged in the same way. Or it's just a little bit faster. So here you have more details. Okay, I will leave that. Now, if you're interested, you can find it on the paper, and we have also the JavaScript code, which is about one of the clients now in the last version.
What was the main limitation?
The main limitation is that although it is invariant, it is very, very precise. Is that sometimes it is too much precise. So if you have to achieve a very high precision rate, you can do it. But then you have to train the system. If you want to have some tolerance, like for instance here, let's say if you have little variations, let's say for the fast forward, if I'm doing just, I'm of course exaggerating, but if I have just something like this, it will say, no, there is a difference here between 2 local triangles, so this will be different. But as long as you do it, even if you have something like this, if you have little variations in this way, this is no problem. But if we have one local, at least it will, well, the score will not be that different. Maybe they will say that here you have a problem and this will give you a percentage of 10%, but at least it's very sensitive. Sometimes it is too sensitive, I would say.
And how sensitive is it to the sampling? I can imagine that also makes a huge difference. If this
That's
is not
right.
nicely synchronized, then your triangles might be messed up somehow.
That's the key question for the moment, is that we have tried different samplings, whether they are with the same distance, the same time, or a combination. The best way is with the same distance. So this is called isometric.
Yeah.
Especially because of the sampling problem like this one. Okay, now in the last part I would like just to give you a few references about gesture sets. We have seen some of the gesture recognizers, not all of them. Today there are a lot of gesture sets where you can see recommended set of gestures. On the one hand, it's nice because these gesture sets are provided as a reference, so you can use them or not. But if you want to stick to them, you have to be very precise. The first one that has been introduced was from the X stroke, and as you can see, for instance, if you want to use A, you have to issue this one. The small a is that one, then for B you have 4 possibilities, 3 for the uppercase and 1 for the lowercase, and you have a bunch of them. So again, the system can recognize all of these variations, but the end user has to learn and to remember all of these gestures. That's the drawback. If the user is introducing a in another way, no chance, unless it is there. The nice thing is that all of these gestures are there, and they are distinguished enough to be well recognized. You have them also for letters, for digits, for signs, for basic, like, again, you have a flick, like a simple letter, or you have also for marks. If you remember, a mark is a combination of flicks.
And they're all single strokes, right? These ones are...
And they're all only unistrokes, yes.
Yeah.
So that's also a drawback, but you have a complete set of them. Also for small commands like meta or comport, key as also a gesture counterpart. So if you want to say cut, and you remember that cut is Control X, so control is this one, and X you can do that. So this can be questioned, but although this gesture set has been very popular until I would say the mid-90s, these days it's no longer used. Second one that is very interesting is consists of the set of gestures, which are a little bit more sophisticated, I would say, recommended by Microsoft for office automation. So initially they were released for tablet PC, but they are roughly something like this. So for many commands, like cut, copy, paste, insert, delete, reproduce, cancel, do, undo, redo, so they have defined a reference gesture. So the nice thing is that it is a standard for Microsoft application in principle, so any Windows-based application that is compatible with that should have the same gesture. But again, some gestures are questionable. To erase, maybe many people will just scratch. But do you know why cut is this gesture? I didn't know until somebody from stenography told me that this is a common gesture in stenography to indicate I made a mistake, so I have to insert something. So this is the curly Q or the double curly Q to make something repeated. So these two gestures are extracted or inspired by the domain of stenography, but since I don't know the gesture from stenography, I didn't know. But now that I know, maybe I will remember them, I don't know. So you have many simple gestures like circle, caret, double caret, forward, etc. Again, you have also the flicks that I told you, like for directions, up, down, left, and combined. So when you combine flicks, you can have marking menus, or etc. But these are a little bit more complex to retain. Like for instance, right up. What does it indicate? It's very physical. So it's very fast to produce. It's accurate to recognize by recognizer, but it's not easy to remember in the head because, well, right and up, what does it mean? Maybe this one looks like L, but this one, I have no idea. So it's difficult to establish a mapping between the gesture and the command. But at least that's the advantage of it. They're all standardized. If you're interested to use them, Microsoft is also releasing a framework that you can download from there, which is ready. You have it in C# or in Visual Basic, and I think it's maybe some other actions, some languages. And for instance, you can attach any action. So this is an example that they are giving. For instance, if you do a flick on the top, it will make a drag. If you do a flick on the northwest, then it will copy. Paste is there. I don't know why, but again, any choice is questionable. Nice thing is that it's straightforward, but it's not perfect. Another page that I like very much is this one from Adrien Delay. He compiled all datasets on gesture that I know. So if you go to that page, I will give you the slides, link to the slides, so that you will be able to download the slides and don't worry about that. And then you can see many of the gesture sets. Some of them are completely dependent on the domain, like the Nick icon. So those gestures were issued for the domain of security. Some others are shape-based, some others are digit-based, so you have many datasets. The problem of today is that all of these datasets, they are all in different formats, different expression, and different level of details. So what we are trying to do, and this is now a student working on that, is that all of these datasets, they're in different formats. Sometimes they are in CSV, sometimes in text, sometimes in XML, sometimes in JSON, sometimes with different degrees of precision. So instead of having all of them in heterogeneous format, we are working with a unified format so that you can use only one recognizer and you can cover them all at once instead of having them separate. Okay. So there are also guidelines, but I will come back on that next week. So as a conclusion, I would just say, I want to say a few things. You have seen the gesture recognizers, and today they are quite efficient, so you can really rely on them. like especially $P plus is the most accurate one. If you have a low-end device or like a smartwatch or let's say a device which is not equipped with a very strong processor, then you may want to use $Q, which is the optimized one. But today there is still no benchmarking. We don't know which one is the best in each condition. This is very challenging. The problem of formats, every recognizer uses its own formats. So if you want to use, let's say, the gesture set from Microsoft on the $Q, you have to convert everything, which is a nightmare. It's not complicated, but in the end you can spend hours, if not days, just for that. So we are working towards a unified format so that you can use any dataset on any recognizer. Gesture sets, you can see they are widespread, but they are not always accessible, and more, I would say, more risky. Some of them are damaged. So, for instance, when you download some of them, well, apart from Microsoft, etc., but there are some web pages where you can download from some datasets, and sometimes the files are corrupted, or some templates are missing, or they have different, well. And today, we are trying to maybe to launch an idea, and this is something that I would like also to discuss with Professor Singer, is as opposed to other domains like in LREC, there is no grand challenge where people meet in a room, we give them a bunch of data sets, and we all try to compare all of our gesture recognizer and see which one is the best for which condition. Nobody is the best, for sure. But probably this one is the best for that part, that one is better for that one, etc., etc. Like for instance, we compare at some point also 4 sets, and I will finish on that. Uppercase letter, A, B, C, D, then lowercase, A, B, C, then digits, 1, 2, 3, which are pretty common, and then Greek letters like alpha, beta, delta, gamma, etc. So interestingly is that for uppercase letter, $1 was the best, because it's used unistroke, and as long as you're unistroke, A here is not, but if you write A like this, it is the fastest, the most accurate one. But $1 is the worst for the lowercase. So in that case, the $P plus was the best, surprisingly. For the Greek letters, the FTL, which was O, was the best for accuracy. Not for speed in that time, but for the accuracy. And this one, for digits, especially in many configurations, like for the 7 this way, it was $Q. But again, it depends also on the device. We have not yet computed that. So today, we have not yet a table where you can, for instance, you as a professional developer or a professional in this area, you don't have a table where to say, okay, this one is the best because I'm using this and that, and you're sure that you will be using the most performant recognizer today. At least you can use $P plus for sure, but it will not be the best for all of them. So this is still a challenge today where we have to work together. So that's all for today. Thank you very much again for coming today and for your attention. And really, I like to finish with this cartoon. Is that you have this person say, can you look at this 3D user interface? And it's a guy in a box acting with some gestures and say, well, this is a very cheap prototype. Why? Because we didn't have time to really prototype a 3D interface with gesture, because we had to produce a prototype very fast. So we use this guy, and then the director says, how can you operate it? Yes, with this remote control. So next time, I will more or less present you, that will be also interesting, a series of case studies where we used gestures. Sometimes it worked, sometimes it didn't work, and I will try to explain why. Or sometimes it worked, but it was not accepted. So the goal of using gesture is not gestural interaction. The goal of doing so is not necessarily to introduce gestures. This is not the ultimate goal, is to try to invent or to introduce a user interface that is more efficient than a graphical one. And I will show you an example from a restaurant where we completely redesigned the user interface with gestures. We proved that it was more efficient, more enjoyable, and even more fun, but then they decided, nope, we'll throw away, we'll not use it. Why? Because they say if we have to replace all of the tactile screens with your stuff on all our restaurants in Belgium, it will cost I don't know hundreds of thousands of euros. So it's just too expensive for us. So we keep like this. So that was a case where it didn't work. Thank you very much again for coming today, and see you next time. If you have any also particular questions or curiosity, don't hesitate to send me to drop me an email.
So we will also make the slides available, and if the video recording should have worked out, I think we will also place that somewhere.
Okay,
so that we can
that's great. Thank you very much for that. I wish you a good afternoon.